All right, well, welcome back to the final contributed session of the afternoon. Please correct my pronunciation. We're going to be hearing from Bertuel Tangue Ndawa from the University of Ngaoundere in Cameroon, who's going to be telling us about infinite lifting of an action of symplectomorphism group on the set of Bi-Lagrangian structures. Thank you so much.
Thank you so much for this opportunity. Before all, I would like to thank the organizer of this workshop. We introduce our talk with the following 3 questions. What is it? That is Bi-Lagrangian manifold. That is F1, F2 is a pair of Lagrangian foliation on a symplectic manifold M omega. To do what? Bi-Lagrangian manifold are area of geometric quantization, Kosovo-Wilmer cohomology. If we have a Bi-Lagrangian structure omega F1, F2, we can generate a paracalar structure that is F squared is identity. G is defined like this, and F and G commute in this sense. We can define a dynamic on Bi-Lagrangian manifold. How to do it? We are going to show it in this talk. More precisely, we are going to explain this diagram. Before to explain our results, we present some definition, notation, and preview results. A K-foliation is a collection of disjoint non-empty connected immense K-dimensional submanifold, so that the property in blue is verified. Note that in this case, for every x in M, Sx is called a lift. The set of section of a foliation is defined in 2.1. The Lie bracket of 2 sections is defined as 2.2. Note that the completely integrable property means that the Lie bracket of 2 sections in the set of sections of F belongs to F. If the manifold is endowed with a omega that is two form non-generate antisymmetric, that is a symplectic form, then we say that a foliation is Lagrangian when the set of orthogonal section is equal to the section of F. Sorry. When we have a Bi-Lagrangian manifold, we have a decomposition 2.4. We are going to introduce an important object on Bi-Lagrangian manifolds, called Hess connection or Bi-Lagrangian connection. Before we introduce in 3.1 and 3.2 respectively the transversal or commutative. The Hess collection is defined from theorem 3.1. This connection was explicitly defined by diffeomorphism in 1919. An important Bi-Lagrangian structure called affine Bi-Lagrangian structure or affine Bi-Lagrangian manifold can be defined by in definition 3.3 as a Bi-Lagrangian manifold with Hess connection whose the curvature, the tension curvature is 0. The set of affine Bi-Lagrangian manifold is defined in theorem 3.3. A connection is flat if only if we have property 3.7 and 3.8. Note that if we have a affine Bi-Lagrangian manifold, the whole space can be used to define the Kosovo-Wimber cohomology, because we need that the curvature, the tension curvature is vanished to define a Kosovo-Wimber cohomology. We are going to define the action of symplectomorphism on a Bi-Lagrangian structure. Before to do it, we observe that 4.1 and 4.2 define the action of symplectomorphism group on the set of vector field and the set of connection respectively. Lem 1 show how to push forward a Bi-Lagrangian structure omega F1, F2. With this lem, we have theorem 2, who will define the action of symplectomorphism group on the set of Bi-Lagrangian structure. The inclusion 4.4 all. That means if the initial structure F1, F2 is affine, then the push forward structure is affine also. Now we are going to define, to present the leaf of Bi-Lagrangian structure. If we have a Bi-Lagrangian manifold then the leaf is defined on the trivial bundle like this, 4.5. We just take the exterior derivative of theta. The result is also Bi-Lagrangian manifold. Note that theta is the one Liouville form, defined is 4.7. We precise in 4.6 the lift of a Bi-Lagrangian structure F1, F2. As a consequence, the leaf of Bi-Lagrangian structure, this leaf can be lifted again on the cotangent, the trivial bundle of M times R exponent to N. That is a Bi-Lagrangian manifold can be lifted infinitely on a successive bundle, trivial bundle. Now observe that a symplectomorphism on a symplectic manifold can be lifted hat Vafi on a trivial bundle, trivial bundle. The previous theorem show that a Bi-Lagrangian manifold can be lifted as a Bi-Lagrangian manifold with the space, the bundle trivial. Now is the natural to ask that how does triangle lift, that is the action of symplectomorphism group on the Bi-Lagrangian structure, can be lifted on the trivial bundle. The second question is, what is the relationship between the leaf relation and the initial relation in our sense? Theorem point 1 is an answer of the first question, and proposition for point 4.2 is an answer is to the second question. We think that we can extend this result to all Bi-Lagrangian structure. The initial diagram shown in the introduction is constructed. Note that if we take the symplectic form on the trivial bundle as the exterior derivative of the Liouville one form, then the leaf as the leaf of a Bi-Lagrangian structure is a affine Bi-Lagrangian structure, independent on the fact that the Lagrangian structure, the initial Lagrangian structure is affine or not. But to have the push forward as an affine, if the initial structure is affine, then the push forward structure is affine also. Thank you for your kind attention.
Thank you very much. Let's all thank the speaker virtually with whatever emoji you have at your disposal. Are there any questions for the speaker? You can either type them or unmute. Okay, if there are none now, I'm sure you'll have other chances that you can check up with your speaker. Just as a brief announcement, what is to come, there is a break now until 4 o'clock